Hi everyone, myself Dr. P. Soumya, working as an assistant professor in the Department of Chemistry at Institute of Aeronautical Engineering College. Today I am going to discuss about wetter electrochemical corrosion and types of electrochemical corrosion. In this session I am going to cover the topics electrochemical corrosion, mechanism of electrochemical corrosion, types of electrochemical corrosion, and what are the factors affecting the rate of corrosion. So what is wet or electrochemical corrosion? So wet or electrochemical corrosion is common type of corrosion which occurs under wet or moist conditions. So wet corrosion means, it is presence of water. So wet or moist condition. Moist means it should contain moisture. Moisture means water. So this type of corrosion occurs in presence of water or moisture. So it is observed when a metal in contact with a conducting liquid and two dissimilar metals are dipped partially in aqueous corrosive environment. So first, when a metal is in contact with conducting liquid, either that is water, oil, like that, otherwise two dissimilar metals are dipped partially in aqueous corrosive environment. So due to this type of corrosion occurs. So the wetter electrochemical corrosion involves formation of anodic and cathodic areas, presence of conducting medium, and also corrosion of anodic parts takes place. Means at anode corrosion takes place. At anode corrosion takes place, and the formation of corrosion product closer to the cathodic area. The formation of corrosion product closer to the cathodic area means in this type of electrochemical corrosion. So if we take one metal, if we place in a moist environment, so when we place this metal into the moist environment, so this will undergo electrochemical corrosion because of moisture and forms some parts of this metal can act as anode and some parts of this metal acts as cathode. So one metal only, one is acts as cathode, second one is acts as anode. So the corrosion will take place at anode, means at anode oxidation takes place, means loss of metal is taking place at anode. The formation of corrosion product takes place at cathodic area. At anode, corrosion takes place. At anode, corrosion takes place. At cathode, corrosion product is accumulated. Corrosion product accumulated. So this is about electrochemical corrosion. So electrochemical theory of corrosion. According to this theory, when a metal comes in contact with a conducting liquid, a galvanic cell formed within the metal. So some parts acts as anode, rest act as cathode. If we take one metal, if we place in a conducting liquid, if we place in this conducting liquid or like that water, oil, like that, so this metal acts as a galvanic cell. Means in a galvanic cell we are having anode, cathode, electrode. Here conducting liquid acts as electrolyte, and in metal some parts acts as anode and other parts acts as cathode. So because of that, this metal acts as galvanic cell. The atmospheric gases and humidity present in the corrosive environment acts as electrolyte. So corrosion of anodic part takes place due to oxidation at anode. So at anode oxidation takes place. So corrosion of that metal, anodic metal, takes place. The electrochemical theory corrosion is explained by taking rusting of iron as an example. So for explaining this electrochemical corrosion, so we are taking rusting of iron as an example. Rusting of iron. rusting of iron as an example. So the anodic reaction. So anode means oxidation takes place. So all we know that at anode, oxidation takes place. So here we are taking iron as a metal. So at anode, what is it taking? Metal is undergoing oxidation and forming metal ion and electrons. Fe is converted into Fe plus 2 and 2 electrons. So the cathodic reaction in the electrochemical corrosion depends on the pH of the corrosive medium and depends on the availability of oxygen and also at different pHs of the corrosive medium. So the cathodic reaction occurs in two ways. First one is hydrogen evolution. Second one is oxygen absorption. Oxygen absorption. So at anode, oxidation takes place. Metal undergoes oxidation and forms metal ions. But cathodic reactions occurs in two ways. First one is hydrogen evolution. Second one is oxygen absorption. So first one is hydrogen evolution. For this, all the metals above hydrogen in the electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evolution of hydrogen. So this type of corrosion takes place in acidic conditions, in acidic conducting medium, acidic conditions. So means here the metal, when it is placed in acidic solution, this type of cathodic reaction takes place. That is, hydrogen evolution takes place when metal is placed in acidic solutions with the evolution of hydrogen. So it occurs in acidic environment, and here also we are taking example of rusting of iron for explaining the hydrogen evolution. Here at anode, we know that oxidation takes place. Here iron is converted into iron plus 2 and 2 electrons. These electrons flow through the metal from the anode to cathode. Anode to the cathode, where H plus ions acidic solution are eliminated as hydrogen gas. Here what we are taking? Here we are taking one metal and we are placing in a acidic solution. In acidic solution. In this, some parts are acts as anode, some parts are acts as cathode. So here at anode, oxidation takes place. Here we are taking only one metal, so this is converted into Fe plus 2 plus 2 electrons. So at cathode, reduction takes place. Here reduction of H plus ions in this conducting medium. Here we are taking acidic solution, means acidic means H plus ions containing solution. Either it is HCl or H2SO4 or any other H plus ions containing acidic solution. In this is having H plus ions, and these can undergo reduction and forms hydrogen gas. So 2H plus accepting electrons and forming hydrogen. Here this is gas. So here evolution of hydrogen is taking place. The overall reaction at anode and cathode is Fe plus 2 H plus gives rise to Fe plus 2 H2. Here this is the metal. Here in this in this type of electrochemical corrosion, anodic area is large, cathodic area is small. Cathodic area is small. Here at anode, oxidation is taking place. Here iron converted into iron Fe plus 2 ion. Here also same. So in the total, this metal is converted into anode and cathode. So see, in this type of corrosion, anodic area is large, cathodic area is small. Here H plus ions are undergoing reduction and forming hydrogen gas. In this type of mechanism, cathodic reaction takes place in acidic solution when we placed a metal in acidic solution. So second one is oxygen absorption type. Oxygen absorption type. Here rusting of iron in neutral aqueous solution of electrolytes like NaCl solution. So in the case of hydrogen evolution, the rusting of iron in acidic solution. Here resting of iron in neutral aqueous solution. So it should placed in neutral aqueous solution such as sodium chloride solution. In this presence of atmospheric gas oxygen, it is a common example of this type of corrosion. Rusting of iron in neutral line in the presence of atmospheric oxygen is a good example for oxygen absorption type electrochemical corrosion. So, the surface of iron usually coated with a thin film of iron oxide. However, if the iron oxide film develops some cracks, anodic areas are created on the surface. So, while the well metal parts acts as cathode. Well metal parts act as cathode. So, we know that if a metal placed in a atmosphere, so this will react with the atmospheric gases such as oxygen, like that. In this here we are taking oxygen, so it will react with oxygen and forms metal oxide. Metal oxide, here we are taking metal, that is iron, so it is will form iron oxide. Iron oxide. If this iron oxide film is not stable, some pores and cracks will form in the this metal oxide layer. So in this, some from the pores, the oxygen will go into the pores and it will react with the metal. So the well parts means that not cracked parts of the metal can act as cathode, and that is not undergoing corrosion. The parts are exposing to the environment, means the parts at pores that will act as anode. Means here anodic area is very small. Anodic area is very small, but here in cathodic area is large. In the case of hydrogen evolution, reverse. So cathodic area is very small, anodic area is very large. In the case of oxygen absorption time, cathodic area is very large, anodic area is very small because of the cracks and pores of the oxide film. At anode, so oxidation takes place. At anode, oxidation of iron takes place and forms Fe plus 2 and 2 electrons. At cathode, the liberated electrons are intercepted by the dissolved oxygen. So here we are taking the rusting of iron in neutral aqueous solution in presence of oxygen. So this is having some oxygen molecules, and these electrons reacted with oxygen and forms hydroxide ions. So these Fe plus 2 ions and OH minus ions undergoes reaction and forms FeOH2, ferrous hydroxide. So if enough oxygen is present, ferrous hydroxide easily oxidized to ferric hydroxide. Here Fe plus 2 is forming at anode, OH minus is forming at cathode. So this will form FeOH2. If we have more oxygen in that place, here again it will react with oxygen. This iron hydroxide react with oxygen and water and forms ferric hydroxide, Fe2O3 plus H2O. Fe2O3 plus H2O. So this is the yellow rust. This is the yellow rust of iron. Here ferric hydroxide is converted into ferrous hydroxide is converted into ferric hydroxide. If the supply of oxygen is limited, the corrosion product may be even black anhydrous magnetite. So if we supply is limited, so it will convert to Fe2O3 is converted to Fe3O4, that is black color rust. So in the case, this is a metal, and here we are taking this is the metal, and here this is exposed to the neutral aqueous solution and oxygen. So at anode, oxidation takes place and it is converted into iron plus 2 ions. But at cathode, oxygen is reacted with electrons and forming hydroxide ions. These two hydroxide ions and iron is converted into ferrous hydroxide, then ferric hydroxide, that is the rust of iron. So this is about oxygen absorption type mechanism. Differences between dry and wet corrosion. So dry corrosion, wet corrosion. Dry corrosion is, it occurs in dry condition, means without moisture, without water. It occurs in wet condition. It should presence of water should be there. Presence of water should be there. If the corrosion takes place due to direct chemical attack, corrosion is known as dry corrosion. If corrosion takes place due to direct chemical attack, not electrochemical attack, is called as dry corrosion. If the corrosion takes place due to electrochemical attack in presence of moisture or conducting medium, so that is called as wet corrosion. So for wet corrosion, it should contain moisture and conducting medium. And in this, direct chemical attack takes place. So this dry corrosion is explained by absorption mechanism. Wet corrosion is explained by electrochemical mechanism. Dry corrosion occurs on the heterogeneous and homogeneous surfaces. But in case of wet corrosion, it occurs on heterogeneous metal surfaces. This dry corrosion is uniform corrosion, and that corrosion, wet corrosion is not uniform. Here, anode corrosion takes place, cathode not corrosion takes place. It is a slope process and it is a fast process. The corrosion products accumulate at the place where corrosion occurs. In the case of dry corrosion, corrosion product accumulate where the corrosion takes place. In the case of wet corrosion, corrosion takes place at anode, but corrosion products accumulate near the cathode. This is the differences between dry and wet corrosion. Types of electrochemical corrosion. First one is galvanic corrosion. Second one is differential aeration corrosion. First one is galvanic corrosion. Second one is differential aeration corrosion. So this differential aeration corrosion again divided into waterline corrosion and pitting corrosion. First, what is galvanic corrosion? This is also known as differential metal corrosion. Differential metal corrosion. In this corrosion, two different metals participated. It is also called as bimetallic corrosion. Bi means two. Bi means two. This corrosion is also called as bimetallic corrosion. Galvanic corrosion occurs when two dissimilar metals, if we take iron and copper, these are two dissimilar metals. Like this, where this type of galvanic corrosion occurs when two dissimilar metals having different potentials are electrically connected and jointly exposed to the aqueous corrosive environment. So this type of corrosion occurs when two dissimilar metals having different potentials connected electrically and jointly exposed to the environment. This type of corrosion takes place. The metal with the lower potential acts as anode. So all we know that the metal which is having the reduction potential is low reduction potential is acts as anode, and it undergoes corrosion. The metal with higher potential acts as cathode and it is protected. The metal which is having higher potential, it is acts as cathode and it can be protected. So this is galvanic corrosion. So example of galvanic corrosion is iron pipes coupled with copper couplings. Iron pipes coupled with copper couplings. So in that we are having two different metals having different potentials. In the example, this iron is having minus 0.44 volts and this copper is having 0.34 volts. Means here this is having less electrode potential. That's why this iron is acts as anode. Iron is acts as anode and it undergoes corrosion. Whereas copper is acts as cathode and it can be protected. It does not undergo corrosion. And it is protected by iron. So in the example, This iron is acts as anode, undergoes corrosion because its potential is less than that of copper. If anodic region is small, it leads to the severe corrosion. It leads to the severe corrosion. So, the galvanic corrosion is controlled by using a pure metal, and using metal closer in galvanic cell, and making sure that anodic metal should occupy large surface. Anodic metal should occupy large surface. So we know that anodic region is, if anodic region is very small, it leads to the corrosion. So making sure that anodic metal should occupy large surface. Due to this, we can control the galvanic corrosion. So next one is differential aeration corrosion. Differential aeration means aeration, oxygen, different oxygen levels. So differential aeration corrosion also called as oxygen corrosion cell. It is a type of electrochemical corrosion that occurs when a metal in contact with a conducting medium, and it is exposed to the uneven supply of oxygen on its surface. So metal should expose it to the conducting liquid, and also it should conducting liquid and should expose it to the uneven supply, not even uneven supply. Uneven supply of oxygen. Uneven supply of oxygen. So this type of corrosion takes place when metal in contact with conducting medium and also expose it to the uneven supply of oxygen on its surface. As a result of uneven supply of oxygen, an oxygen concentration cell is formed within the metal. So because of uneven supply of oxygen, the oxygen concentration cell is formed within the metal. So the part of some metal which is exposed to the less oxygen concentration acts as anodic area and gets corroded, while the part of metal which is exposed to relatively high oxygen concentration acts as cathodic area of corrosion cell and it is protected. The part which is exposed to less oxygen, that is acts as anode. The part which is having exposed to high concentration of oxygen, that is acts as cathode. So that anode is undergo corrosion, cathode is protected. So at anode, metal converted into metal ion, and at cathode, that is more oxygenated, at the water is converted into hydroxide ions. So moisture and oxygen will react with each other in the presence of electrons and forms OH minus ions, hydroxide ions. So the cathode is protected, anode is undergoing corrosion in the case of differential aeration corrosion due to uneven supply of oxygen. Examples of this type of corrosion include drop corrosion, waterline corrosion, pitting corrosion, crevice corrosion, etc. So also the areas below nuts, bolts, joints areas covered by dust particles and welded areas are suffered from this type of corrosion. The nuts, bolts, joints, areas covered by the dust particles and the welded areas are suffered from this type of corrosion, from the differential aeration corrosion. So first one is the differential aeration corrosion, again divided into two types, waterline corrosion and pitting corrosion. So first one is waterline corrosion. This waterline corrosion is a type of differential aeration corrosion, and it occurs when a metal is partly submerged in water or metallic tank is partially filled with tank. So when metal is partially dipped in the like this, metal is partly submerged in water, otherwise metallic tank. So otherwise metallic tank partially filled with water. So the part of metal below the waterline is poorly oxygenated. Here below the waterline, poorly oxygenated. Here also poorly oxygenated. So this can act as anode. These parts of acts as this part is acts as anode, and the parts which are above the waterline is more oxygenated and acts as cathodic area. Here cathodic, this will act as cathode, in this case water tank, and in the case of this rod, here this can act as cathode. This can act as cathode. So anode can undergo oxidation and forms metal ions and undergo corrosion. So the corrosion occurs in the anodic area, and simultaneously reduction of oxygen to hydroxide ions occurs at cathodic area. At anodic area, if we take iron tank, it will convert iron plus 2 ions, and at cathodic area, so oxygen converted into hydroxide ions. Oxygen is converted into hydroxide ions. Hydroxide ions. These hydroxide ions and iron plus 2 react with each other and forms rust. This is the corrosion. And the corrosion product is formed closer to the cathodic area. This type of corrosion occurs in water tank, ocean liners, etc. This type of waterline corrosion occurs when a metal is partly submerged in water or metallic tank partially filled with water. The part of metal which is poorly oxygenated acts as anode that can undergo oxidation and undergo corrosion. The parts which are highly oxygenated, that is more oxygenated parts, are acts as cathode and forms cathodic area, and they can be protected. So this type of corrosion occurs in water tanks and ocean liners, etc. Next one is pitting corrosion. This is also differential aeration corrosion. Pitting corrosion is a localized form of corrosion resulting in the forms of pinholes and pits. So resulting in the form of pinholes or pits like this. So when a small cracking, breaking of protecting film on the metal surface occurs, the small anodic area and large cathodic areas formed. So all we know that if metal undergo corrosion, metal oxide or some metal oxide layer will form. If it is having some pores and cracks, the small anodic areas will form. And large cathodic areas will form. So in this type of corrosion occurs when small cracking, breaking of protecting film on the surface occurs. Small anodic areas and large cathodic areas are formed. The inner area of it is less aerated. So the outer surface of the metal will aerated. So inner surface area, in the pores and cracks, the area is small anodic area that can act as an anode. Here, because of less aerated, less oxygenated area, the more oxygenated area acts as cathode, that is rest part of that metal can act as cathode. So therefore the inner area of the pit acts as anode undergo corrosion, while outer surface of the metal acts as cathode and it can be protected. So pitting may also be due to galvanic corrosion. First one is the preferential attack of environment on metal or alloy may lead pitting. The preferential attack of the environment on a metal of an alloy may lead this pitting. So example of this pitting corrosion is alloy of copper and tin. The scratches on the cathodic coatings also favor pitting. So in this, small anodic areas are there because of breakage of that film, the metal oxide film. So the small areas are which is exposed to the less oxygenated let oxygen and it undergoes corrosion. More oxygenated areas protected. So factors affecting rate of corrosion. So first one is nature of metal, nature of the corrosion product, and nature of environment. Nature of metal, nature of the corrosion product, nature of environment. So nature of metal. So first one is position of the metal in galvanic series. So we already know that galvanic series and electrochemical series gives real and useful information regarding the corrosion behavior of the metal. So when two metals are electrically combined and exposed to corrosive environment, so depending on the electrode potentials, the anode will undergo corrosion, cathode will undergo corrosion, protected. The anode, the metal which is having low potential acts as anode and it can undergo corrosion, whereas the metal with the higher potential acts as cathode and it can be protected. So second one is purity of the metal. In general, higher the purity of the metal, purity of the metal, lesser the rate of corrosion. So purity of the metal, if metal is pure, it does not undergo corrosion. Means in general, higher the purity of the metal, lesser the rate of corrosion. The zinc of 99.5% purity undergoes corrosion at a rate of about 5,000 times more compared to the zinc 99.999% purity. Means purity is making a crucial role in this corrosion. So next one is hydrogen over voltage. If the hydrogen over voltage of the metal is low, the rate of corrosion will be high. Hydrogen over voltage is low, whereas over voltage is low, the corrosion rate will be high. So it depends on the relative areas of anode and cathode. The rate of corrosion is more with the combination of large cathodic area and small anodic area. So the rate of corrosion depends on directly proportional to the cathodic area by anodic area. The rate of corrosion is directly proportional to cathodic area. So if cathodic area is more and smaller anodic area is small, the rate of corrosion increases. So next one is nature of surface oxide film. If the corrosion product formed is stable, non-porous and strongly supported layer is, and that will prevents the corrosion. So nature of oxide film. If the formed oxide layer is stable, that can be act as a protective layer to the metal. If the corrosion product is formed is highly unstable, the metals do not undergo corrosion. If the product formed is volatile, the metal undergo severe corrosion until that metal completely destroyed. If the corrosion product is soluble in medium, to which it is immersed, corrosion of the metal occurs with a faster rate. So in presence of medium, the corrosion rate is very faster. So next one is nature of corrosion product. Solubility of corrosion products, and second one is volatility of corrosion products. In the electrochemical corrosion, if the corrosion product is soluble in the corroding medium, the corrosion proceeds faster rate. If the corrosion product is soluble in the corroding medium, means if corrosion product is soluble, so the fresh metal is exposed to the environment and further corrosion takes place. So the corrosion proceeds at faster rate. In the corrosion product, if it is insoluble in the medium, it interacts with the medium to form another insoluble product. Then the corrosion product functions as a physical barrier, means it can act as a protective layer to the metal and it decreases the rate of corrosion. If corrosion product is soluble, corrosion takes place. If corrosion product is not soluble, it can act as a protective layer to the metal and it does not undergo further corrosion. So volatility of corrosion product. If the corrosion product is volatile, means it can evaporate easily and it will by leaving the underlying the metal surface exposed to further attack and severe corrosion takes place. This causes rapid and continuous corrosion leading to the excessive corrosion. Example of this is molybdenum oxide. Molybdenum metal is undergo corrosion and forming molybdenum oxide layer. This is a volatile. So The oxidation is takes place again and again, and until the molybdenum is destroyed. So next one is nature of environment. First one is effect of humidity, second one is effect of temperature, third one is effect of pH. Higher the humidity, higher will be the rate of corrosion. Moisture, higher the humidity. Moisture, if moisture is more, so the rate of corrosion is also more. The moisture can act as a solvent for oxygen, H2S, SO2, etc., which are present in our atmosphere to furnish the electrolyte essential for setting corrosion cell. So the gases like H2S, SO2 increase the acidity of medium by the dissolution of water. When these gases react with water, it will form acidic media to the metal, and the rate of corrosion is increases because of this presence of humidity. Therefore, the rate of corrosion increases as humidity increases. Effect of temperature. So, all we know that the rate of corrosion increases with increase of temperature. And also effect of pH. The rate of corrosion of metals is much faster in acidic pH than alkaline or neutral. But atmospheric metals like aluminum, zinc undergo severe corrosion in basic medium. So most of the metals, the corrosion of most of the metals much faster in acidic pH than alkaline. But some metals like aluminum and zinc can undergo severe corrosion even in basic medium. So the rate of corrosion depends on the effect of pH. So these are about factors affecting the rate of corrosion. And thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.